Nothing you think is real is real. The ancient Greek philosopher Democritus wrote, "By convention, there is sweetness. By convention, bitterness. By convention, color. In reality, only atoms and the void." Modern physics doesn't add much to this. The Standard Model has no more than 18 particles, framing nearly every scientific theory of nature we have. Physicalism, the majority view among philosophers and scientists alike, asserts that everything, mind, body, consciousness, love, and so on, can be reduced to causes arising from the interactions between these fundamental building blocks. Yet, we do not experience the world in these microscopic terms. We experience the macroscopic world, where dualism and other supernatural concepts feel real. Does something connect these two worlds, resolving this seeming contradiction? Indeed, it is quantum physics that bridges the inaccessible microscopic world of fundamental particles and the macroscopic world we experience, and it reveals how our perceptions create an illusory reality out of the impenetrable microscopic substrate. However, before diving into the depths of these revelations, we need to read the fine print. The interpretation of a speaker's message is influenced by a complex interplay of factors, including the listeners and the speaker's implicit biases, social context, past experiences, and personal beliefs. Often, we don't know what those are. I'm making assumptions about you, the listener, and you are making assumptions about me, the speaker. These assumptions are used to fill in the gaps and make predictions about the message I'm trying to convey. In fact, a great listener does most of the work in a conversation, and it's no easy task. So let me tell you a little bit about myself so the prediction engine up there has less work to do. And I'll start at the end. So I'm a professor at the University of Technology Sydney's Centre for Quantum Software and Information. I get paid to teach, mentor students, and conduct research, and that happens mostly in the field of quantum artificial intelligence. I'm also the founder of a startup company that is democratizing access to quantum computing by building educational tools like the desktop quantum computer emulator seen here on the slide. And finally, I'm an author. I write popular science books for children and adults alike. So these two are an odd juxtaposition, to be sure, but there's a common thread in explaining complex topics in an easily digestible and relatable form. See, when I was a teenager, books like Stephen Hawking's A Brief History of Time or Brian Greene's The Elegant Universe painted this vivid picture of a quantum birth of the universe bubbling with the quantum foam and parallel brains. And like many bright-eyed enthusiasts, these stories sparked a lifelong fascination with quantum physics. But as I delved deeper, mastering the textbooks and digging into cutting-edge research, I realized that all of those early stories were entertainment at best. They exaggerated or sensationalized the weirdness of the quantum world, leaving no room for the nuance and complexity that brings true revelation. You see, quantum physics is not so much a theory of a fantastical hidden reality as it is a mathematical model that helps answer practical questions about the world. My goal is to tell you useful stories, not a collection of mind-bending paradoxes born of quantum mysticism, stories that are both practical and compelling, but also grounded in the rigorous mathematics and experimental evidence of quantum physics. Stories that inspire wonder and curiosity without resorting to exaggeration or sensationalism. I come by this view honestly because in reality, I'm not a physicist or an author, I'm a mathematician. My over 10 years of formal training were in applied mathematics, and I've carried this implicit philosophy of the applied mathematician with me ever since. While there are plenty of applied mathematicians in the world, there are not many that reach a popular audience. So I trust that this point of view will be quite new to you. I hope by the end, you'll be able to adopt this perspective with me, seeing quantum physics not as a source of fantasy, but as a tool for understanding why the fantasy arises in the first place, and what questions are worth asking in a reality invented in your own mind. So let's get started. Have you ever seen a painting up close? Well, a painting is just a surface of woven fiber that has absorbed a mixture of resin, solvents, and additives. Different parts of the surface have different additives called pigments that absorb specific wavelengths of light and scatter others. Occasionally, a member of the species Homo sapiens perceives this scattered light and calls it art. The difference between this art and the stained canvas fiber is what is known as the beholder's share. While the idea dates back to the writings of early 20th century art historians, it was Marcel Duchamp who dared to quantify it, saying that an artist only completes 50% of the work. The remaining 50% is done by the perceiver. Trying to quantify it exactly is a bit silly, of course, but the point remains. Art is a collaboration between the artist and the beholder. An artwork is not a fixed entity with a singular meaning. Rather, it is completed by the perception and interpretation of its viewer. This concept highlights the interactive nature of viewing art, where the observer plays an active role in creating the art's significance. What if reality itself is like a piece of art, waiting to be completed by our perceptions and interpretations? You are not the artist or the architect of reality, but you are the beholder. In other words, rather than being a passive observer of the world, you are an active participant in completing it, interpreting it, and giving it meaning, just as you would a piece of art. You might think that looking at art entails a passive observation of physical reality that has been encoded with some meaning or message that is identical for all perceivers. What actually happens is far more complicated. Let's suppose that I am looking at the Mona Lisa in Paris. Well, I am looking at it. I'm not really seeing the piece of art, but instead the light that has scattered off of it. The characteristics of this light, its intensity and color, for example, depend on the properties of the art and the original light source. Someone standing next to me presumably sees the same piece of art, but is, in fact, receiving their own portion of the scattered light. Provided that the environment and perspective are roughly the same for both of us, the characteristics of this light relevant to perception are the same for all practical purposes. The lens in my eye focuses light onto the retina, which is lined with light-sensitive cells called photoreceptors. These cells convert the light signals into electrical signals that are transmitted via the optic nerve to my brain. Here, they are processed by various visual centers that interpret the attributes such as color, depth, movement, and form. This processing relies on the physical properties of brain cells, called neurons, which are nearly identical for each individual as dictated by part of the 99.9% of DNA common to all humans. However, the way all 100 billion neurons are connected in each brain is unique to that individual. My unique neural network encodes my personal experience, memories, and how my emotions will manifest. Transient brain states caused by the myriad stimuli of everyday life inhibit or enhance neural pathways, all leading to this final psychological response that completes the piece of art. To further illustrate the point, let's consider various optical illusions. So one famous example is Rubens' vase. In the illusion, you might see either a vase or two faces in profile, depending on your perception. So I'm just going to pause for a moment while we all stare at this together, and I'll tell you that when I stare at it, what I see flips back and forth between the two alternatives about once every second or so. But the image doesn't actually change. Only my interpretations of it does. Nor is there a correct answer. This is no actual vase and no pair of faces. I just created the black profile and put it over top of the last slide, not intending for them to be faces or to outline a vase. So these realities, these ideas are invented in my own mind. So clearly art, as it's completed by the beholder, is as subjective as it is active. But we can all agree that the Mona Lisa, the early 16th century painting by Leonardo da Vinci, currently sitting in a basement in Paris, is objectively real, right? I mean, it's right there. Maybe my imperfect sight can't see the atoms in the canvas for what they are, but surely with the aid of some scientific instruments, I could do it. And if that were true, at least in some augmented form, I would be what is known as the ideal observer or ideal beholder, someone who could ascertain the true objective nature of the work of art. Such an ideal beholder would be an ideal observer of the world, someone who could ascertain the true nature of reality itself. Indeed, physicists have been attempting this for the last 100 years or so, probing the universe at finer and finer scales in the ultimate quest for the God's eye view of the cosmos. But what they found instead disturbed them. Of course, I am talking about quantum physics. Now, if you heard or read about quantum physics before, you might have already suspended disbelief, expecting to be told wild and mysterious things about the quantum world. But let's just step back a moment and remind ourselves just how strong our belief in objective reality is before I tell you that it doesn't exist. The belief in objective reality is fundamental to human cognition and crucial for interacting with the world. Recognizing a stable, objective reality enhances our ability to navigate, survive, predict outcomes through understanding cause and effect, and applying consistent rules. Evolutionarily, those that could comprehend and plan based on unseen aspects of their environment had an obvious survival advantage, and that facilitated and developed this obviously heritable trait. As anyone who has played peekaboo with a child knows, the delight and surprise on a baby's face when an object or person reappears is a testament to their emergent understanding of object permanence. So this simple game reflects the developmental milestones where children begin to grasp that objects and people continue to exist even when they're out of sight, a concept that forms the foundation for trusting and engaging with their environment. Without such constructs, simple tasks like driving a car, cooking a meal, holding a conversation would become impossible. This vision of reality serves as a framework that simplifies the complexity of the world around us, providing a coherent story that aligns with our sensory experiences and cognitive capabilities. In modern times, societies are built on a shared understanding of the world. Language, laws, education, and science all rely on assumptions that there is this common world that we all experience together. This shared belief is reinforced through communication and education, helping maintain social cohesion and cooperative behavior. Indeed, some argue that conflict stems from an incompatible worldview and different stories about what is real that each of us has bought into. So our intuitive conception of objective reality was enshrined in what you could say law by the principles of classical physics, established by figures like Isaac Newton, for example. This framework views the world as a collection of objects and phenomena that behave in predictable, deterministic ways under the laws of physics. Newton's laws depict a universe where time and space are absolute, and objects have specific measurable properties such as position and momentum, unaffected by the observer's perception. This offers a comforting view of objectivity, certainty, cause, and effect. For example, whether I touch the table in front of me or I see an apple fall from the tree, Newtonian physics assures me that these objects are there regardless of my observation. They are real, tangible, and objective. Except that's not true. In the early 20th century, quantum physics was introduced as an ad hoc way to address problems that classical physics couldn't explain. With esoteric names like the black body radiation problem and the photoelectric effect, which I won't go into, and you can find other videos about, Max Planck kicked off the idea of quantization of energy in 1900, followed by Albert Einstein's 1905 proposal that light behaved as quantized energy called photons. A decade later, Niels Bohr developed a quantum model of the atom, presenting a system where electrons occupy fixed orbits and change orbits by emitting or absorbing these photons. And that explained not only observable facts like spectral lines that appear when you shine light and lasers on atoms, but also explains the stability of all matter around us, why you don't fall through the floor. In 1924, Louis de Broglie proposed that not just light, but all matter exhibits both these wave-like and particle-like properties, assigning a characteristic wavelength to everything. This concept was experimentally confirmed shortly after through electron diffraction, demonstrating that seemingly solid matter experiences wave interference. That is all what's known as the old quantum theory. It was seen as providing corrections to classical physics. The dual nature of it was frustrating. Einstein, for example, said, "It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomenon, but together they do." So this is known as wave-particle duality. And what he was pointing at was that we have these two theories. You have to use the wave theory sometimes and the particle theory other times. And there isn't one unified theory that explains all of the characteristics of the phenomenon. And he was talking about light in this case, but it applies all, through de Broglie's work to everything. So at the time, most and probably all physicists assumed that there was going to be some seamless melding of these new aspects with classical physics. And it was just a matter of finding a way to make that possible. But in 1927, Werner Heisenberg introduced the uncertainty principle, stating that certain properties of a system cannot simultaneously be known to arbitrary precision. And the most famous pair is position and momentum. So where a particle is and how fast it's going. So quantum uncertainty dictates that you can't know where something is and how fast it's going with arbitrary infinite precision at the same time. You can only know one or the other, or both with some imprecise knowledge. That kind of seems technical and pedantic, but Heisenberg himself was quick to point out that they had far-reaching philosophical implications, and it basically challenged the deterministic nature of all of classical physics. So in Newtonian physics, exact knowledge of the present allows the future to be calculated. This is the law of causality as was understood during Heisenberg time. So this law of causality isn't violated, it's just not applicable, since uncertainty relations don't allow you to have exact knowledge at any moment in time to be able to predict the future or the past. So Heisenberg said, since all experiments obey the quantum laws and consequently the uncertainty relations, the incorrectness of the law of causality is a definitely established consequence of quantum mechanics itself. Basically, he was saying that there is no cause and effect in the world. Einstein famously would have none of it. In the late 1920s, he famously debated Heisenberg, Bohr, and others, attempting to show a logical inconsistency in the uncertainty relations. He devised clever and elaborate experimental proposals, Gendaken experiments or thought experiments, aiming to show that the position and momentum of particles could be ascertained using a single apparatus. But each time, Bohr demonstrated the flaw in Einstein reasoning, including one famous example where he used Einstein's theory of relativity, in particular that clocks in changing gravitational fields experience time dilation, against him. So in each case, the experimental arrangement to ascertain one property always rendered another uncertain. Chaining three of these experiments together, or imagining three of them being chained together, reveals that the active measurement must also have a physical effect on the thing under investigation. As Max Jammer put it, in brief, an experiment is a violent interference with the regular course of nature. In science, measuring and testing things is often invasive. In medicine, a biopsy is an obvious example of a measurement that alters the organ being tested. Measuring the temperature of a room requires the transfer of heat from the room to the thermometer. Measuring the air pressure in a tire requires at least letting a little bit of it out. These are all examples of what is called the observer effect, the change in the thing observed due to the act of observation. And scientists understand this observer effect very well, as it's a small part of the many types of errors that can occur during an experiment. However, most scientists also believe that an experimenter acting in good faith is one who's making the best attempt to eliminate all errors. The ideal observer is one who could ascertain the true value of the measured quantity without any disturbance to the thing being observed. Uh, this is sort of a ruling out bias, for example. And this is exactly what the uncertainty relation rules out. But we can go further and ask, if we can't define properties of things, in what sense do they even exist at all? In what sense can we even talk about them? Eventually, Einstein admitted that quantum physics was a consistent theory with numerous successes, but he maintained that it was not a complete theory because he could not specify an objective reality. His friend remarked, "We often discussed his notion of objective reality. I recall that during one walk, Einstein suddenly stopped, turned to me, and asked whether I really believed that the moon exists only when I look at it." Einstein argued that the moon surely has a definite position in the solar system, regardless of whether or not it is being observed. In this view, there is a true objective reality out there. If we were clever enough and careful enough, we could know it. Einstein envisioned definite things in the world that obey some laws of physics. They have done so since the dawn of time and will continue to do so regardless of whether or not any observer is around to witness them. The moon didn't just appear as soon as humans looked up in the sky and saw it. But Bohr and others contended that a large part of the issue comes down to language. Bohr was famous for his impenetrable prose. At one time, he said the following: "In the case of quantum phenomena, the unlimited divisibility of events implied in such an account is, in principle, excluded by the requirement to specify the experimental conditions. Indeed, the features of the wholeness typical of proper quantum phenomena finds its logical expression in the circumstance that any attempt at a well-defined subdivision would demand a change in the experimental arrangement incompatible with the definition of the phenomenon under investigation." So what on earth could he mean by this? Well, the gist of it is this: what you measure is defined by the procedure used to measurement. You can try to probe deeper and deeper, but each iteration requires a different experiment. At some point, the experiment itself has been altered so much that it no longer serves the original goal. In short, experiments define the thing under investigation. And if you change the experiment, you change the thing. Heisenberg put it more succinctly. He said, "If one wants to clarify what is meant by position of an object, they have to describe an experiment by which the position of an object can be measured. Otherwise, the term has no meaning at all." So what does it mean for the moon to exist? Well, presumably, it at least requires that it have a position, in addition to all the other properties you might ascribe to it. And quantum physics forces us to confront what ought to be an obvious fact. Measuring properties requires interaction. How could it be otherwise? Complete isolation between observers and the world? There would be no world at all to behold. John Wheeler emphasized this point of view in his typical quotable fashion. He said, "No phenomenon is a real phenomenon until it is an observed phenomenon." You might think that, say, kicking a large stone reveals the reality of the stone, but it only reveals that probing your environment requires an interaction. In essence, the observer effect is inevitable at the level of quantum things. The fundamental phenomenon from which all of the things we observe, the entire universe, is constructed. Pascal Jordan took this to its logical conclusion, saying, "Observation not only disturbs what has been measured, but produces it. We compel particles to assume a definite position. We ourselves produce the results of experiments." Wheeler called this the participatory anthropic principle. And it goes that reality is the answers we get from posing questions to nature. Without questions, nothing would be answered. Hence, we are participants in the creation of events. More than that, though, duality dictates that the answers depend on the questions we ask. Choose to measure position, and position manifests in the world. Choose to measure momentum, and something else manifests in the world. If we choose position, then momentum is something that never was and now never could be. Wheeler had a clever analogy for the participatory nature of reality, which he likened to a game of what he called reverse 20 questions. So let's imagine some version of this game being played out. So there are 20 people in a room, right? And you walk into the room, or one person walks into the room, and they're meant to find out what these people have agreed to think about. So 20 people in the room agree on an object, like, for example, a coffee cup, and one person has to discover what that is by asking yes or no questions. So a variant on 20 questions. So what might they ask? So they say, is it something you can drink from? Yes. Is it made of metal? No. Is it found in most homes? Yes. Can you hold it in your hand? Yes. Does it have a handle? Yes. So through these questions, the person might deduce that the object is indeed a coffee cup. But now here's the bait and switch. The 20 people never actually agreed on an object in the first place. Instead, they simply answered each question in a way that didn't contradict the previous answers. The person asking the questions arrived at coffee cup, but this conclusion wasn't based on any pre-existing object. Instead, the object was created through the process of asking and answering questions. So this analogy illustrates Wheeler's point. Reality isn't something that exists independently of our observations and interactions. Instead, it is shaped and defined by the questions we ask and the answers we receive, highlighting the participatory nature of the reality that we complete. It is often said that serious scientists are in pursuit of the true nature of reality. This certainly evokes some grand, ambitious pursuit to uncover the deepest truths of the universe, one that combines the rigor of science with the profound questions of philosophy. And while acknowledging the earnestness of this romantic vision of exploratory quest, it is ultimately unrealistic. Reality is not out there, it's in here, or at least that's where it begins. Our popular notion of reality is not objective, it's intersubjective, tied up in our collective stories that include culture, history, tradition, science, conspiracy, and so on. Some may argue that denying objective reality is a cop-out, a way of dismissing the hard work of trying to understand the world. They might liken it to the fox in Aesop's fable, who dismisses the grapes he can't reach as sour. But this perspective misses the point entirely. The grapes aren't sour. There are no grapes. Those who cling to the notion of objective reality are on a misguided quest, reaching for grapes that aren't there. They are still the greedy and hubristic fox, though, unfortunately. Whereas if we acknowledge the subjective nature of reality, it doesn't diminish the value of our experiences or the importance of seeking understanding. Instead, it invites us to explore the richness and diversity of human perception and interpretation. The moon is art. Otherwise, like pigments stuck to a canvas, it's just another arrangement of molecules. What we typically consider to be part of reality, moons, desks, chairs, stones, and so on, is simply an agreement between observers about the interpretations of our perceptions. The moon is real because I have expectations about what I will see in the night sky, and those agree with the expectations of mostly everyone else. Moreover, in 2024, we also intersect in our mental models of what that object is, a large ball of rock and metal rather than a ball of cheese. No one holds in their mind the true nature of the moon, and that's impossible anyway. Something is there, whether there's an artist, Who knows? But we complete it. We bring about a personal reality that we then share. In some dimensions, the moon makes for rather boring art. Parts of it leave no room for interpretation. Like the Mona Lisa, which we all agree is a portrait of Italian noblewoman Lisa Gherardini, in the beholder's share lies in finer details. The smile is like the shape of the moon's Maria, which appears as a face to some and as a cat to others. But even finer details at the level of atoms, no two people can ever agree. This is because there's no quantum reality beyond our perceptions. What is essential about art is its relative permanence. The Mona Lisa sits in Paris, as it has for the last 200 years, and displays roughly the same set of brushstrokes as it always has. This information is copied and replicated for the eyes of the beholders in the gallery, but also for the virtual observers of the digitized versions appearing all over the internet. If the brushstrokes disappeared as soon as Da Vinci painted them, it wouldn't be art for the now obvious reason that there'd be no beholder's share. The words I'm speaking now quickly dissipate into the medium of air in this room, but they are real because you are here. No two of you will agree in every detail on your interpretation of them, but there is some ambiguous consensus on what I've said. Understanding this, I've wisely written them down and they're being recorded, and that makes them more robust to this relentless onslaught of quantum interactions. The fact of the matter is that the real Mona Lisa, the actual painting in Paris, won't last forever. And this is thanks in part to the observer effect. Every time a particle of light strikes the painting, it imparts its effect, eventually leading to the decay of the pigments and fibers. Each particle of light is then taken by an observer, a beholder of the art. Whatever that particle did to the painting can never be recovered. So each particle, each quantum of light is the beholder's quantum share. With each share we take, we destroy a part of the world. It is the price we pay to construct this intersubjective reality. So by taking on the perspective of the applied mathematician, one who seeks to tell useful stories, we have found our way through quantum physics to participatory realism, which rejects that an objective, observer-independent reality is out there waiting for us to have a God's eye view over it. More than that, this viewpoint makes clear that denying objective reality is not an act of resignation, but a humbling and empowering shift. Humbling in its admission that we are never in possession of the truth, empowering in its recognition that we are active participants in creating an experienced reality through these stories. Adopting this philosophy comes with the responsibility of creating stories, explanations, models, theories, guides, or whatever you want to call them, grounded in practical knowledge, evidence, and utility. So I invite you to go out there and tell useful stories. Thank you.